Welcome to the flock. Let's dive into Dalton's law and calculations for finding partial pressures of a specific gas if you're only given moles. Stick around to see how it's done. So Dalton, this guy here, basically said that if you've got a container that has a bunch of different gases in it, how do we figure out what the pressure is attributed from each gas within that container? And he said, hey, well, I think the total pressure is just the sum of each individual gas's individual pressure. And he called those partial pressures. So each gas has its own partial pressure, and that all attributes to the overall pressure of the container that the gases are stored in. We'll represent this mathematically by just saying the P total, that's just the pressure total here, is equal to the sum of the various partial pressures of each gas present. So say gas A, gas B, gas C, for example. In the most simplest of contexts here, we're literally just going to add the partial pressures together. So let's give this question here a try in context to blast furnaces. If the total air pressure is 0.99 atm, that's our P total for our equation. The partial pressure of carbon dioxide is 0.05 atms. That would be one of our P1s. I can just call this PCO2. And the partial pressure of hydrogen sulfide is 0.02 atms. I could say that that would be P2 instead of 2, I'll just put H2S for hydrogen sulfide. And then what the question is asking is, what is the partial pressure of the remaining air? So we're assuming there is some other unknown remaining amount of air, our X variable like in math, that we're solving for here. So all we have to do is plug and chug. We have 0.99 atms, set that equal to P1 is our 0.05 atms for the CO2, plus 0.02 atms for the hydrogen sulfide, plus X, that's what we're solving for, the remaining gas. So now when we add together these two here, we get 0.07 plus X on the right-hand side, set equal to 0.99. Now this is different than the other gas laws because the other gas laws are dealing with multiplication and division, whereas this is dealing with adding and subtracting. So to get this X alone, since it's adding on this side, we're going to need to undo add and subtract. So let's just subtract the 0.07 from both sides here. And then we see that we get an X value equal to 0.92 atms. So basically what that's saying is that the partial pressure of any of the remaining air altogether in the blast furnace would be 0.92 atms, or atmospheres of pressure. So basically, if you're given the partial pressures of various gases, you literally just add them together. Of course, a common wrench that you might encounter in this whole scenario that seems oh so easy is that maybe they give you partial pressures in different units of pressure. So maybe they give you a P1 that's in millimeters of mercury, they give you a P2 that's in atms, they give you a P3 that's in torr, and in which case you would have to convert them all to be the same unit before you can add or subtract them. That's about as complicated as this kind of problem can get. In fact, I'm going to throw one of those wrenches at you now. Notice in this question, when you're going to solve it, the final total gas pressure, I want it in millimeters of mercury. Recall from previous videos that 760 millimeters of mercury is equivalent to 1 atm. If you don't know where I got that conversion factor, please check out my video on gas terms and units linked in the description below. But for now, pause this video and give this calculation a try. Ready, go! All right, let's check your answer, see if you got it right. All right, so hopefully you got 66.12 millimeters of mercury as your final answer for this calculation. Now, before we level up to the calculation that I showed you at the beginning of the video, where you're only given moles and you have to solve for partial pressure of a gas, let me show you a really kick-butt, ninja-style demonstration of partial pressures. Grab yourself a large sheet of newspaper and a ruler without metal edging in order to become a chemistry ninja. If I put the ruler on the table with nothing holding down the backside and I hit this side, it flies off the table. However, if I put the large sheet of newspaper over the top of this ruler, making it possible for the air in the room to press down on the larger surface area and hold this ruler down, watch what happens. 1, 2, 3. Give it a try, and you too can be a chemistry ninja. This ruler stood no chance against the pressures of the air surrounding it, and the chemistry ninja, Duckonta. So why did this experiment even work? How is it possible that flimsy newspaper could help me break this ruler in half? Without the newspaper, there was nothing holding the ruler down on the other side. But the newspaper increased the surface area over the back of the ruler in order to hold it down using nothing but the air molecules, the air pressure in the room around it. No tricks, no gimmicks, just science. So this is where I see a lot of chemistry students trip and struggle around these concepts. And I think these concepts are easiest approached when you understand the reason why we have a certain equation the way we do. So if we're starting with Dalton's law equation, which we just learned, as the pressure total is the sum of all the partial pressures of the gases present, then if a question's asking us what's the partial pressure of one of these gases in moles, well, shucks. This would be easy to solve if we had the total pressure, which we have here, and we had partial pressures given of the other gases, but we don't. All we have are moles. So how do we end up going from moles of a gas to partial pressures of each gas? Well, let's think through this logically. We know that the sum of all the moles present contributes to the total pressure. So what we can say then is that the pressure total is due to the total number of moles present. But from here, we need to get a partial, not a total. So we want to know just the partial amount of carbon dioxide, for example. What's carbon dioxide's contribution to the overall moles? Well, if we know that the total moles are 5 plus 3 plus 1, and we know that 5 out of those is carbon dioxide, this is literally just like a percent, a part per whole. So if we were interested in just CO2, what we'll call the mole fraction of CO2, which will represent by an X of CO2, that would technically be just saying, okay, that's the part that's of CO2 divided by the whole, just like what we would do to find a percent. Here, our whole would be our NT, the moles in total, and the part would be the moles that are just coming from CO2. So in this case, our mole fraction would just be 5, which is the moles from CO2, divided by 5 plus 3 plus 1. That's all of the moles together. So we get a value of 5/9 as our mole fraction. Okay, that's great and all, you might be saying, but 5/9 of what? What is the whole that we're looking at here? Remember, we're trying to find a partial pressure, and if we want to find a percent of something, we need the whole. Well, don't we have the whole pressure? We sure do. We have the total pressure, the 1.05 atms, and we know that we want the part of it. Are you catching my drift here yet? So we should know then that the partial pressure of CO2 would be like saying, hey, what's 5/9 of the overall pressure, 1.05 atms. So that would look like this. Total pressure times our X CO2, which is our mole fraction. This is the common way that it's represented in most chemistry textbooks, and I think that's where most people get it confused, because it looks confusing. Like, where did this X come from all of a sudden, right? But really, it's just as simple as thinking about it being a percent of a percent, basically. You're just taking the percent of the moles and figuring out what the percent of those moles are for the total pressure. So now, if we literally say 1.05 times 5/9, that should give us the partial pressure of CO2. And our value for that would then be 0.583 atms. All right, now that you've seen me do one partial pressure, the partial pressure for carbon dioxide, here, go ahead and give the calculations a try to find the partial pressure for nitrogen and the partial pressure for hydrogen, using the same setup we just talked about. I also included the basic setup up here in case you needed to reference back. Pause the video now. All right, let's check your answer for nitrogen first. All right, so hopefully you got a partial pressure for nitrogen of 0.35 ATMs and a partial pressure for hydrogen at 0.11667 ATMs. Now here's the great thing about these specific calculations. You can always check your work and make sure you got the calculation correct. If you did it right, these three pressures together should equal the total pressure of the container, because we're assuming that all three of these gases, carbon dioxide, nitrogen, and hydrogen, are in the same container, therefore contributing to the total pressure according to Dalton's law. So the three of these added together, if you plug and chug into your calculator, sure enough, gives you a value that's basically 1.05 ATMs. So we know we did it right. Think you can do one from start to finish now? Go ahead and pause the video now and give this calculation a try before I give you the answer. Ready? Go! All right, so you should have gotten those values for the partial pressures of each gas respectively. Let's check our work to make sure we did it right, because who wants to get the answer wrong on the test? So we know that our partial pressures, when added together, got us close enough to the total pressure of 3.5, so we know we got it right on the test. Make sure you understand these concepts thoroughly by testing yourself and answering these calculation questions before moving onwards. If you'd like to know the answers to these questions, please comment below and I'll be sure to let you know if you got them right. In this lesson, we learned how Dalton's law basically is just addition. We can find the total pressure of a container or a system just by adding up the partial pressures of each gas. Now, it's important to note that the units of each gas need to match. So that's where this question is particularly tricky. You have to convert them all to one chosen unit and then add them together. It doesn't matter which unit you choose, just pick one and make sure they're all uniform. Then we also learned how to calculate the partial pressure of a specific gas if all we're given is moles of the gases and a total pressure, just like this question here. In which case, we're going to use an equation that is the partial pressure of whatever gas that is in question is set equal to the total pressure, which is always going to be given to you, multiplied by the mole fraction of the gas in question. And that mole fraction happens to be the part per whole of whatever mole of gas we're looking at, in comparison to all the moles, the whole, that's present. Holy moly! I hope that makes these types of calculations a little less daunting for you. Please give this video a quacks up and subscribe to Duckonta for some more free educational content. Quack you later!
No ducks, no glory.